Great to meet you all. We'll talk about cloud-native GenAI using KServe and OPEA. Me, myself, I'm a technical director at Nutanix, primarily leading the AI initiatives there. On the open source front, I lead a couple of communities, including Kubeflow, ML Common Storage, and on the KServe side as well. With me, Gavrish, he's ML engineer in the Nutanix AI team. He's KServe maintainer and a contributor to various projects, including Envoy AI Gateway. So in this talk, we'll briefly cover about why LLMs are hard to manage from the app layer and from your infrastructure layer. What are the possible use cases? What are the challenges that you see? And what the possible solutions are to that? And how do we scale from there? So why LLM is hard? So let's talk about from the infra side of things. Right? So by definition, LLMs are really large. We are talking about parameters which are ranging from billions, millions to terabyte scale. And you would have heard about the recently announced OpenAI model, GPT or OSS, which is again 20 billion and 120 billion. So the primary problem there is to find the right resources required to deploy these models at scale. And if you see most of these models, when you scale, you need to understand how much context length you want to support and what the model size is. So in general, sizing for various set of accelerators, including GPUs, TPUs, require expertise there. And depending on the workloads, the response time is very critical. For example, if you have a chat-like application, SLAs are a bit tight. When you have batch inferencing workloads, you can run for hours and days. It doesn't really matter. And when compared to traditional models, the request-based auto-scaling doesn't work. Take an example of a traditional image model. Your request length is always fixed. While in case of LLMs, you're talking about having varying request length. Say at this instant, you can ask a question in chat, which would be just a few bytes. In the next instant, you would be asking to summarize an entire document, which can take 100K or 1 million tokens in a single go. So in the very first state, your GPU will compute in no time, while in the second case, GPU will be busy for next 5 minutes. So in that case, how do you scale request while looking at the pattern? So that is where your request-based auto-scaling doesn't work. In general, you need much more advanced algorithms to figure out what's the right auto-scaling strategy there, maybe looking at the token-based, et cetera. And this often leads to heavy GPU underutilization, which is something that you don't want at any moment, primarily because you are paying for GPU per hour, right, in cloud or even in on-prem. And you need to have support for a variety of hardwares, including GPUs, TPUs, and custom ASICs, which are very, very common now. And from your app layer, the primary problem is you have a wide range of use cases. You don't have kind of like standard end-to-end template which can solve use cases. And you would have seen like many blocks all around talking about too many overlapping frameworks there. And there are no standard interfaces to talk to these use cases, right? For example, I have a document summarization. What is the API that I have to call in order to make it work? And in most of these use cases as well, you need lots of experimentation. To get a POC is fine, but when you want to get that to production, you need lots of experimentation. Take an example of RAG. There are many hyperparameters which have to be tuned in order to make it work, be it chunking, be it number of documents which have to be retrieved, et cetera. And this often gets to larger setup cost because you are talking about app plus infra. And in many of the workflows, including agentic workflows, it is very hard to estimate the final inference cost because it is kind of like an autonomous agent which is happening to make your task right. So if you have used agents, you would see there's a thinking process. You execute, you take action, and it goes in loop. So how do I control the entire cost associated with my inference and the setup? So that is where OPEA comes in. It is open platform for enterprise AI under LFAI. So what you get is composable building blocks for creating multiple generative AI use cases. So think about this way. You have a set of reference blueprints for different common GenAI patterns. It's completely vendor neutral. Think about having multiple layers. Each can be implemented using the standard ones or your custom implementations. For LLMs, for example, you could use OpenAI, AWS, Hugging Face, or the open source LLMs. And you could extend if some support is not provided by default. All the different use cases you are seeing, deep research for your thinking process and then getting your data in a research format, document summarization for summarizing the documents, RAG for talking to your data. You ingest to VectorDB, and you retrieve based on your queries. Translation for translation tasks, code generation for generating code, which is kind of a very popular tool right now. Visual QA for having context from videos and images and talking to videos and images as the context to that. Generating FAQs for your documents, agentic workflows for creating the reasoning process and doing your daily task from end to end. So take a simple RAG example here from a very high level. You have an app service which consists of multiple microservices which talks to the underlying backends. Your retrieval microservice talks to LLMs, the configured LLMs. Embedding microservice talks to embedding models, which you have configured. Data preparation does all your cleanup and pre-processing of data. Re-rank talks to re-rank models, which you have configured. And the entire app that you're seeing is actually a Helm chart, which you can deploy in a single click from the GitHub, which you can take a look at it. And in the data path, it is pretty straightforward. For an application, you provide some data, use an embedding model to ingest into VectorDB, retrieve from VectorDB based on query. You re-rank models. You re-rank documents based on the query. And you take the re-rank documents, provide to a Llama model or any model that you have access to. With the configured runtime, you get the final result. And it can run on Kubernetes or Docker or your favorite runtime as well. So this is good. This is easy to start, but very difficult to scale. So on the left side, you have seen RAG app. There are independent apps. ChatQA, again, application talking to LLM, which is again deployed on Kubernetes. Document summary, again, you have multiple microservices, again, talking to Kubernetes. So here, the bigger problem is your application and the infra layer management becomes difficult. Both are combined together. And what's a possible solution? So can we take the app layer separate and the serving layer separate, which can run on Kubernetes then? So your application developer can focus on the app layer, while your platform admins can look at the serving layer, which is purely on the infra side. So that is where KServe comes in. KServe is a Kubernetes native serving controller on Kubernetes. So if you see, on top of Kubernetes, you have KServe controller, which can work on any accelerator. It can be on NVIDIA GPUs, AMD GPU, or the Intel GPU, or even custom ASICs as well. So what it provides is you give a model of any model format, be it Hugging Face, be it PyTorch, or be it TensorFlow. It creates APIs for you so that you can interact with the models on your favorite runtime. So predict APIs for your non-traditional models, generate APIs for your chat models or your newer GenAI applications. And once you have these APIs, you can do auto-scaling based on your requirements. So as we discussed, for non-LLM workloads, you could use traditional request-based auto-scaling, while for LLMs, there are advanced auto-scaling strategies that we can use from KServe. And in your production setup, once you have rolled out one version, you have an option to do canary and blue-green deployments based on your requirement as well. And you have a flexible model storage backend where it can connect to multiple model storage options. Like, for example, it can be S3, GCS, and variety of options there. So on high level, it provides an inference service CRD, where you specify a model format and runtime, and where the model is located. That's it. It takes care of deploying that model with the runtime. You get pluggable runtime support, VLLM, Triton, and for traditional side, you have TorchServe, XGBoost, scikit-learn. Your model can be on different storage types provided by the storage URI, S3, GCS, Azure Blob, the standard NFS, and Git. And typically in large language models, you shouldn't download models continuously, primarily because we are talking about terabytes of data. So when you want to scale from 2 to 3, for example, you want to have some kind of cache with you and reuse it for the further scaling up and down. That is where model cache comes in, where you can reuse a single instance of model file for your future requirements. And it provides various auto-scaling techniques. And specifically, scale to 0 is very important when you want to save your GPU time. So for example, when you have traffic, you scale up. And when you have idle time, you scale back to 0, saving GPU, freeing up GPU, and saving cost. And it can be based on different GPU metrics that you can configure to. It provides various rollout strategies, as I said. And it is hardware-agnostic. You can run on any accelerator that is possible, be it CPU, AMX, GPU, IPU, etc. So on a very high level, what does OPEA provide on KServe? So if you see, with the KServe layer, you get a scalable, cloud-native, production-grade serving infrastructure, which is primarily looked by your infra admins to scale your serving workloads. While on the top layer, application developers can build various applications, your chat QA, document summary, RAG, where these are modular GenAI workflows, which are purely written by your application developers. So you try to isolate the responsibility and the concerns of app layer and infra layer separately.
Thanks, Johnu. So we'll quickly go through a demo. So in the demo, I want to show how easily you can start deploying an OPEA app. We're going to start with a DocSum app, and how you can use KServe and its features to scale it. Okay. So here, I'll be using the Helm charts to install OPEA. So initially, OPEA comes with its own VLLM. So now VLLM gets installed using the Helm chart, and we'll check whether the pods are running. And next, we'll start deploying the OPEA app, which is the DocSum app. And even there, we'll use the Helm chart. So here, in the single Helm chart, you will get all the things required to install the app. It can be the app service, the like monitoring service, or any other things needed to run day one operations. So now the OPEA app also got deployed, and you're seeing the status of it. And we port forward it so that we can send some requests and see how we can see the monitoring dashboards, other things. So here in the request, we just send, OK, this is my message. Summarize this to me. And I'll send multiple requests so that I can show it in my dashboard easily. Oh, sorry. I kind of skipped it. Yeah. So this is the Grafana dashboard, which OPEA installs on its own. And here, it provides you all the metrics which are LLM specific. If you see here, the latency, time taken to output tokens, latency, the token throughput, and also the scheduler state. So now we had hit some requests. So you can see some scaling here on the request side, and there'll be some throughput also scaling. So this is the OPEA app installation. Okay. So now how the OPEA app installation brought you its own app, which was easily installed using Helm chart, and it got its own VLLM, which is single instance VLLM. So now I want to scale it. So supposedly I have too many requests coming in. I want auto scaling. I want some level of like specific GPUs to use for specific use cases, all those things, which KServe brings in. So now I'll deploy KServe and attach it to the OPEA app so that I can use the KServe auto scaling use case. So to deploy KServe, we'll use the KServe CID, which is the inference service CID. So here you could see that its auto-scaling class being used is HPA. And then we are using 5 replicas as the max and 1 replica as the min. We are still using VLLM as our serving engine. And we are running, mainly to note here is we are running on CPU. So everything is CPU inference and we are not using any GPU. And it's running a Llama 3 8B model, and we are using some CPU around 4 and 24 gig RAM. So once I apply this ISVC, the KServe controller will pick this up, and it'll launch a KServe predictor pod. The KServe predictor pod initially will go it in min replicas, and then as we bombard some traffic, we'll start seeing that there'll be some monitoring being done on the HPA side. So if you see, the first pod has come up, and now we'll start bombarding more traffic. So I'll pour forward the service, and I'll start bombarding traffic to this pod. The main thing to look here is that the scalability metrics was on CPU percentage. So it's on 50% CPU. If it goes above that, I want it to scale. So now I'll go and check the HPA stats to see what's the live status for a duration. So when I started bombarding, it was around 37% CPU usage, and it hit 100%. So immediately after the next duration, it has to scale up. So now we can see the desired pods has gone to 2. And if I go back to my pods list, you can see there's one new pod which was container creating stage and has started to come up. And this will continue until you keep bombarding requests. If the average CPU stats keep on increasing, your pod will keep scaling. So in our case, we just showed how to scale to 1 to 2. And now if we stop sending requests, the stats will start reducing, and you'll start the pod again going to the min replicas. So I'll fast forward the state. So the duration can be set on your own use case. In our case, the scale-up duration was every 15 seconds to 1 minute, and the scale-down duration was around 5 minutes. So once it hits the scale-down period, which was around after 5 minutes, you can see the desired count was 2 prior, and now it's back to 1. And now when the CPU usage was continuously below the 50% threshold which we had set. And now if I go back to the pod setting, you can see there was one pod which has started terminating and has reached a completion state. So these are the features which KServe brings in inherently, and you can all control this using a single CRD. Yeah. So next part is, OK, we showed you how to start with a simple LLM deployment, right? But LLM runtimes are not enough. You need LLM-specific features to come in. We need some things which will make it truly distributed. You can scale it in a large scale. The models are getting huge. If you see the DeepSeek model, the Llama 4 model, they don't fit on single node, which has 8 GPUs. You need a multi-node setup. So that's when all the LLM-specific features started taking place. So initially, when VLLM came, it improved single node very well. But now we need multi-node. We need to split the VLLM nodes. We need multiple solutions to scale this whole LLM case. So the first thing which the community came up with is, can I have a single CRD which is LLM specific? Can I do routing through this single CRD? Can I do PD, which is PD means, can I split the VLLM node into prefill and decode? Because prefill is very compute-intensive work. It's the start part when you get a prompt till the first token generated. And second is decode, which is more memory-bound. So can I split it and use specific resources for those? Second thing is, if I have a very large model and my one node has only 2 or 4 GPUs, how do I fit it? So that's when I need multi-node inferencing. And the routing comes in picture. Now, which particular node I should pick? Which particular deployment is best suited? That's when the gateway layer comes in. So gateway layer integrations helps in the routing step. And even the auto-scaling, the traditional auto-scaling does not work anymore. Because my GPU utilization, how much tokens I'm generating, how much KV cache I have in my thing, which particular KV cache node is better, all those things are more important than how many requests are being sent to me. So that's when the auto-scaling queries might change. So that's where the KIDA integration will come in. And finally is the KV cache distribution. So the GPU memory is limited. I have generated some KV cache for some other prompt, but now I don't need it. So I can offload it to some other distributed entity. So this is the new proposal for the CRD, which is the LLM inference service. So here, there are 3 layers, which is the router, workload, and the KV cache manager layer. So the router layer is the ingress layer. It is supported by the gateway API. So there are multiple providers which implements this. And along with this, there's something called gateway inference extension, or the LLMD, which is the new project in-house. They call it LLMD scheduler. So what this layer tells is that, can I start my routing for one particular workload depending on some parameters which is specific to my use case? So they got something called, OK, can I use the KV cache? So what prompt is coming? Can I find the best node which has the best KV cache match, and then send a request only to that node, and not go and recreate all this? So that's when the routing layer came into place and became very useful on the scaling end. Next is the workload layer. So workload layer can be PD, as I told you. You can split the VLLM nodes for one specific task, or you can have it as a single node or as a multi-node setup. So it can be based on your workload, but each of this configuration helps in different use cases. And the KV cache offloading. So GPU memory is short. I want to offload into other storage. It can be RAM, disk. And all these events are captured by the KV cache manager, which in turn will help me in my routing further down. So all this is implemented into a single CRD called LLM inference service in KServe, and you can take the default option or operate on, like, go and fine tune, saying that I want this particular gateway, I need this particular settings and all those. So the final layer with all the thing combined, the app layer, the infra layer, and each component of the infra, right? So I'll start with the Envoy AI gateway layer. So this provides you an unified API. So right now it supports OpenAI chat completions. What happens here is, I have some credits in OpenAI provider. I have some credits in Anthropic, somewhere in Google. I want to use a single interface as an entry point, but use all those credits I want. So this layer helps me do that. I can bring in, for my specific thinking use cases, I'll use the Cloud model. But some other use cases, I'll use the OpenAI O3 model. So I can have a single entry point for my applications, but all this can be served with the single routing layer. It also helps with token usage, tracking across providers, and also rate limiting and observability specific. And this main here is the intelligent routing, which is the endpoint picker. So now, if I have self-hosted my LLM, and I've hosted on some VLLM container, which can be in different options, like PD, single node, or multi-node, right? Now, how do I know which particular has the best suited for my need when the request comes in? So that's when the endpoint picker layer helps it. So this layer is aware, and it tells to the router that, OK, for this particular workload, this might be the optimal node which should be taking your request. And if you see on the left side, there's the KServe layer. So the KServe comes with its own controller, which manages the CRDs for LLM inference service. And it also installs KIDA LLM autoscaler with it. There's a model cache layer, which helps in so that you don't have to download the model all the time. I'll download one instance of Llama 4. It's enough. I can use the same cache layer all the time. And the DRA, which will help you in GPU scheduling. The KServe also comes with model registry. You can have your model stored in S3. It can be in any other registries, and you can plug it in as is into the CRD. And last, the KV cache layer, which I already spoke about. So here, the offloading happens if the VLM container feels that, OK, this particular generated KV cache, I don't need it right now for the current request. I'll offload it to the distributed KV cache layer, which is supported by LM cache here. So to highlight all of this here, so our app needs and infra needs are very specific. And you have to use different layers to enable them. So here we demonstrated that if you focus on one particular layer, get it done, and integrate both the layers together, you can have a full-on solution which you can serve end-to-end use cases of your choice. So that's where our talk ends, if you have any questions. And you can hit us up on LinkedIn, myself, Gavrish, and my colleague, partner, Johnu.